10 Amazing Serendipities of the Galaxy. Hello everyone and welcome to my channel. The Milky Way is like a precision-run giant machine, hosting some 100 to 400 billion stars spread across a magnificent disk about 100,000 light-years in diameter. This vast sea of stars not only harbors countless planets and possibilities for life, but also holds unspeakable mysteries, such as the supermassive black hole Sagittarius A*, which sits quietly at the heart of the Milky Way, controlling the balance and order of the galaxy. Have you ever wondered how many seemingly accidental yet amazing phenomena there are in this vast galaxy? From the rhythms of star birth and death, to the dynamic balance of interstellar gas clouds, to the perfectly timed trajectories of stars that seem to be incredibly precise at every step. Is all this pure chance, or does it hide some deeper pattern? As astronomer John Ballou said, "The most amazing thing about the universe is not its infinity, but its order." The magic of the Milky Way lies in these seemingly mundane, yet incredibly precise coincidences. Next, let's explore 10 of the most incredible magical serendipity in the galaxy and experience the beauty of cosmic design. 1. The Milky Way escapes the fate of supergiant galaxies. We often talk about destiny or the chosen one, but did you know that the Milky Way's destiny seems to be a kind of magical coincidence? It escaped a fate that would have made it disappear, becoming a supergiant galaxy. If it had become one of those very large galaxies, we probably wouldn't even be talking about it now, because there would have been no place for life. To understand this, we need to look at what a supergiant galaxy is. Simply put, supergiant galaxies are the largest and most massive class of galaxies in the universe. They typically have trillions of stars that form a massive galactic core and are bound by powerful gravitational forces. The sheer size of these galaxies and the density of stars has an unintended consequence. These galaxies are prone to develop supermassive black holes. Supermassive black holes are huge monsters at the center of galaxies that can be millions or even tens of millions of times more massive than the Sun. These black holes don't just sit there as we might expect, but their gravity is so strong that they can swallow up stars and gas around an entire galaxy. Due to the extreme effects of gravity, the core regions of many supergiant galaxies are usually very depressing, with the birth of stars almost completely suppressed, and the space for star formation almost taken over by black holes. In other words, the core of a galaxy is like a dark zone in the universe, where no stars can form and there is no hope for life. For the Milky Way, this is like dodging a bullet. Because if the Milky Way were even larger, it could have evolved into a similar supergiant galaxy, and as a result would have had a close encounter with a supermassive black hole, forming a galaxy where no new stars could be born. In this case, the Milky Way would not be able to provide sufficient conditions for the formation of stars and planets, and would not be able to flourish as we see it. The Milky Way is now about 1/10 the size of some of the supergiant galaxies, and although it is a relatively large spiral galaxy, its mass, number of stars, and the structure of its core region are just right, and it is not plagued by the overgravity problem that some of the supergiant galaxies are. The right size here is actually quite subtle. When a galaxy is of the right size, it is large enough to accumulate large amounts of gas and matter to facilitate the birth of stars and planets, but not so gravitationally strong that the core of the galaxy becomes too compressed, allowing new stars to form in a more stable environment. It's as if the Milky Way galaxy has been placed in a prime spot, in a cosmic jigsaw puzzle. Galaxies that are too small may not be powerful enough to accumulate enough gas and matter to support star formation, while galaxies that are too large may be too gravitationally constrained to sustain a life-giving galaxy system. The size of the Milky Way, neither too small nor too large, is just right to allow it to both hold a large number of stars and to sustain constant star formation and evolution. To better understand this, we can look at a few examples. There are many supergiant galaxies in the universe that are much larger and more massive than the Milky Way. For example, the Cygnus A galaxy, located in the direction of our neighbor Cygnus, is hundreds of times more massive than the Milky Way. At the center of this galaxy is a supermassive black hole that is billions of times more massive than our Sun. You're probably thinking, that's so big it's scary. Yes, the gravity of this black hole is so exceptionally strong that it swallows up almost all the gas and stars around it, which leaves the core of Cygnus A with little chance of star formation. Astronomers have found that large galaxies like Cygnus A tend to enter a dead phase at the end of their life. The black hole at the center of the galaxy develops so rapidly that it is almost impossible for stars to be born, resulting in a dead galaxy that is like a cosmic ruin. Another example is M87, a typical supergiant galaxy in the Virgo cluster. It also has a supermassive black hole at its center, with a mass 6.5 billion times that of the Sun, and while the core of M87 has a large number of stars and gas, the black hole at its core compresses the gas within the galaxy, inhibiting star formation. Astronomers studying M87 have found that the core of the galaxy is almost in a state of stellar deadness, with a much lower rate of star formation than in the Milky Way. Is it a coincidence that the Milky Way did not go the way of the supergiant galaxies, or is it a manifestation of some law of the universe? This is where it gets really interesting. The history of the Milky Way is not as smooth as what we see today. Billions of years ago, it also experienced collisions and absorption with other galaxies, such as the merger of the Gaia-Enceladus dwarf galaxy. It is this modest collision and growth that has helped the Milky Way maintain a moderate size. Astronomers have a concept called the path of galaxy evolution. Each galaxy goes through different stages of evolution over the long years after its birth. The Milky Way seems to have taken a lucky path, with its size and mass allowing it to both absorb foreign material and maintain a relatively stable environment for starbirth. On the cosmic stage, the Milky Way seems to have avoided the path of death and found an ideal equilibrium. 2. Galactic collision history of the Milky Way. To talk about the collision history of the Milky Way, you have to understand that nothing in the universe is ever at rest. Every galaxy is in motion, and there is always a gravitational pull on each other, which causes galaxies to constantly collide and merge. The history of the Milky Way has not been a smooth one. In fact, it has experienced several major collisions of galaxies, the most famous of which is of course its close encounters with other dwarf galaxies. These collisions did change the Milky Way dramatically, but interestingly enough, they did not kill the galaxy. Instead, they contributed to the growth and evolution of the Milky Way. Billions of years ago, the Milky Way was not as stable and mature as it is today. The Milky Way was like a young galaxy, full of energy and change, and perhaps not as spiralized as it is today. At that time, the Milky Way collided with some other dwarf galaxies, such as the Gaia-Enceladus dwarf galaxy, and the consequences of this collision can be described as far-reaching and complex. According to astronomers, the Gaia-Enceladus dwarf galaxy is a small galaxy that collided with the Milky Way about 8 billion years ago. The collision was not just a meeting of two strands of matter, but a complete annexation. The stars, gas, and dust of Gaia-Enceladus were almost absorbed by the Milky Way. The result? Instead of destroying the structure of the Milky Way, the stars from outside expanded the galaxy's disk and added more stars to the core of the Milky Way. You might ask, don't collisions throw galaxies into chaos or even collapse them altogether? The answer is, collisions are indeed a violent process in the evolution of the universe, but not every collision leads to disaster. In fact, collisions play a crucial role in the formation of galaxies. As you know, when galaxies collide with each other, the relative distances between the stars are so great that the stars don't collide directly. What's more likely to happen is that the gas clouds and dust in the galaxies are violently disturbed, creating new star-forming regions. Such collisions of massive gas clouds often result in dense amounts of material, providing plenty of raw material for the birth of new stars and planets. Specifically, the addition of dwarf galaxies like Gaia-Enceladus adds to the complexity and structure of the Milky Way. Galaxy collisions tend to mix the material of both, a process that is both violent and chaotic, but ultimately beneficial to the long-term development of galaxies. In the process, new stars are constantly being born and the rotation patterns of galaxies change subtly. Not only that, but collisions and fusions are often effective in removing some of the unstable regions of galaxies. For example, when the Milky Way collided with other galaxies, some of the irregular nebulae and clumps of gas that were there were rearranged, which gradually stabilized the structure of the Milky Way, forming the beautiful spiral shape we see today. In a way, galaxy collisions are a delicate balance between life and death in the universe. Collisions change the structure of galaxies and facilitate the birth of new stars, but they also remove factors that may be detrimental to the evolution of galaxies. It is these collisions that keep the Milky Way alive and in evolutionary balance. So, how have these past collisions in the Milky Way been revealed to us? This is a rather interesting scientific process. It is important to realize that galactic collisions and mergers happened billions of years ago, and we can only speculate about this history now through galactic remnants. Astronomers use a method called galactic dynamics to infer past collisions by studying the motions of stars in the Milky Way. For example, by measuring the speeds and orbits of different stars, scientists can find out if they were ever perturbed in some way by external galaxies. Even more amazingly, Astronomers have been able to reveal whether stars in different regions of the Milky Way came from other galaxies by analyzing the composition and age of those stars using the technique of cluster analysis. In 2018, the European Space Agency's Gaia mission made an important discovery. It revealed traces of a collision between the Gaia-Enceladus dwarf galaxy and the Milky Way. By observing the orbits and chemical composition of the stars in the Milky Way, scientists confirmed that the Milky Way had collided violently with this dwarf galaxy in the past. The trajectories of these stars bear remarkable similarities to those of Gaia Enceladus, proving that they were once part of the same galaxy. You may be wondering, will the Milky Way collide with other galaxies in the future? The answer is, it definitely will. In fact, the Milky Way is in the midst of a slow collision with a neighboring Andromeda galaxy. Although the collision is still about 4 billion years away, scientists have been able to predict the outcome of the collision through simulations. The gravitational pull of the Andromeda galaxy and the Milky Way is gradually causing their orbits to change, and eventually they will collide like two giant objects to form a whole new galaxy. This process will take billions of years, but current observations suggest that the collision will not destroy the solar system. The solar system will probably be thrown into a new position, but because the stars are so far away from each other, there will be no direct collision between the stars. However, the collision would certainly bring about large-scale changes. For example, huge clouds of gas could be stirred up again, leading to a peak in star formation. At the same time, the shapes of galaxies would change radically. Eventually, the Milky Way and the Andromeda galaxy will merge into one giant galaxy, which may be named Star of Beauty. 3. Thickness and stability of the silver disk. Did you know that the thickness of the Milky Way's disk is only about 1,000 light-years? Although this number may sound abstract, it is actually full of coincidences and mysteries. Today, let's talk about how many scientific and cosmic mysteries are hidden behind this seemingly simple value. First of all, we have to understand what is the silver disk. Simply put, the silver disk of the Milky Way is a giant pancake of stars and gas, and it is one of the main components of the Milky Way. Think of the lasagna you order at the coffee shop, except that the radius of the pie is about 50,000 light-years, and its thickness is only 1,000 light-years. That's like putting a 1 centimeter thick piece of paper in the middle of a 50-meter diameter soccer field. Amazingly thin, but it's keeping the whole galaxy stable. So what's the deal with this 1,000 light-year thickness? Scientists have studied it and found that it is neither too thick nor too thin, which happens to be a key factor in the ability of the Milky Way to be stable over time and support star formation. Why can't it be too thick? Let's start with an interesting hypothesis. What would happen if the silver disk were thicker than it is now, say increasing to 5,000 light-years? Studies have shown that the thickness of the silver disk directly affects the gravitational distribution of galaxies. If the silver disk were too thick, stars and gas would be too dispersed to come together effectively to form new stars. Like when you try to build a castle out of a loose clump of sand, the uneven distribution of gravity can lead to a less compact structure, which can end up making the galaxy look like a bloated loaf of bread instead of a beautiful spiral disk. Scientists studying other galaxies have found that some unusually thick galaxies really struggle to keep their internal structure stable. As an example, the galaxy NGC 891, about 30 million light-years away, has a silver disk that is nearly 2,000 light-years thick, and as a result, its star formation rate is much slower than the Milky Way. It's like an orchestra where everyone's rhythm is messed up and the tune doesn't sound as harmonious. So why can't it be too thin? Since too thick is bad, wouldn't thinner be more perfect? Actually, not really. If the silver disk is too thin, say only a few hundred light-years, the whole galaxy will become very fragile. Why? It has to do with the gravitational dynamics in the galaxy. A thin silver disk is more susceptible to external perturbations, such as the gravitational effects of neighboring galaxies or the gravitational fluctuations of black holes within the galaxy. These disturbances can cause the stars and gas inside the disk to be torn apart, like a thin piece of glass that cracks with a little force. For example, scientists have observed the Andromeda galaxy, which is about 2 million light-years away, and found that its disk is slightly thinner than the Milky Way's, but it is more susceptible to perturbations from the surrounding dwarf galaxies, and that the edges of the galaxy appear to have a distinctive ripple-like structure. These ripples are the result of the thin disk's difficulty in resisting external gravity. Where does this 1,000 light-year thickness come from? This is the amazing thing about the Milky Way. Scientists believe that the 1,000 light-year thickness is not random, but the result of billions of years of evolution of the universe. Back billions of years ago, The Milky Way was a chaotic cloud of interstellar gas, which slowly, gravitationally, began to gather into disk-like structures. However, the process was not a smooth one. As the gas gathered, it collided, rotated, cooled, and eventually reached a dynamic equilibrium. This equilibrium allows the silver disk to neither disintegrate because it is too thick, nor be torn apart because it is too thin. In an interesting study, astronomers modeled the formation of the Milky Way and found that the sacrifice of small dwarf galaxies also played an important role. When these dwarf galaxies were gravitationally captured and annexed by the Milky Way, their material gradually filled in the thickness of the disk, helping to form the Milky Way's current stable structure. These casualties are like the craftsmen who added bricks and mortar to the walls of the city, quietly ensuring the integrity of the Milky Way. If you think about it, 1,000 light-years thick is kind of like the golden ratio of the universe. Not only does it give the Milky Way a stable structure, it also provides an ideal environment for star formation. Modern astronomers have compared other galaxies and found that this medium-thickness disk is very rare. Most galaxies are either too thick or too thin. The Milky Way, like a master of balance in a universe, has found just the right spot. What's more interesting is that this thickness indirectly aids life on Earth. Scientists have found that if the thickness of the Milky Way's silver disk is off, star formation within the galaxy may be affected. And star formation is a key process for producing the heavy elements that ultimately create life on our planet. One astronomer once joked, if the silver disk of the Milky Way had been a little thicker, perhaps we would now be writing an elegy for the galaxy instead of a paper. Although the thickness of the Milky Way's silver disk is very stable right now, the universe is dynamic. Scientists predict that the thickness of the silver disk could change dramatically in the next few billion years when the Milky Way collides with the Andromeda galaxy. This merger could rip the disk apart and reform it into a giant elliptical galaxy. But perhaps by then, we will have already developed the technology to travel across the stars to witness this spectacular scene. 4. Molecular clouds in the Milky Way. Did you know? The giant molecular clouds in the Milky Way are really like a kind of nursery in the universe, silently nurturing newborn stars. In a seemingly quiet part of the cosmos, deep space is actually a place full of potential for life, and these molecular clouds are the cradles of stars. Molecular clouds may sound a little stiff, but think of them as huge, cold clouds of cosmic dust and gas, made up mostly of hydrogen molecules, mixed with small amounts of helium and other trace elements. Scientists have discovered that there are about 6,000 of these molecular clouds in the Milky Way, and amazingly, they're not clumped together in one corner, but rather, they're skillfully distributed among the galaxy's spiral arms, as if they've been carefully laid out by some invisible force. This distribution is actually very crucial. You can imagine that the Milky Way is like a giant web of starlight, and the molecular clouds scattered between the arms are like soft light bulbs that gently illuminate the star birth process of the Milky Way. The reason why molecular clouds are able to nurture stars is that the gas in them gradually shrinks under the effect of gravity, increasing in density and temperature, and eventually triggering nuclear fusion to give birth to a new star. That said, perhaps you're wondering how molecular clouds were discovered. That's thanks to radio astronomy. Visible light telescopes can't see through this dust, but radio waves do. In the 1970s, astronomers managed to map the distribution of molecular clouds in the Milky Way by observing the radiation from carbon monoxide molecules. At that time, scientists were even shocked by the number and size of these behemoths. Some of them are hundreds of light-years in diameter and have masses millions of times that of the Sun. For example, the famous Orion Molecular Cloud Complex, about 1,500 light-years away from the Earth, spans hundreds of light-years, and is an active region for star formation. The famous Orion Nebula, an extremely young star birthplace, can be seen with the naked eye as a faint glow in the constellation Orion on a winter night. These molecular clouds are so skillfully distributed that they are of great significance to the evolution of the Milky Way. They act as the galaxy's fuel depot, maintaining the star formation rate by providing a steady supply of the materials needed for star formation. If the molecular clouds were all concentrated in one corner, the evolution of the galaxy could become highly unbalanced, with some regions overactive and others dead. Of course, this just right distribution has prompted some scientists to wonder, is it purely a physical process, or is there a deeper pattern in the evolution of the universe? A cosmologist named James Peebles has suggested that the formation of the large-scale structure of the universe may be influenced by the distribution of dark matter. In other words, the seemingly random distribution of molecular clouds may have an invisible hand pulled by dark matter. Let's talk about the spiral arms of the Milky Way, the stage for the distribution of these molecular clouds. The Milky Way is a barred spiral galaxy, and the arms are like giant vortexes of starlight, along which the molecular clouds are distributed, giving the Milky Way a fascinating spiral shape. Interestingly, this distribution also helps explain how the Milky Way has maintained a relatively stable star formation rate for billions of years. Imagine an interstellar fireworks show, in which a molecular cloud is constantly collapsing to form new stars, which are then shaken by supernova explosions to create new molecular clouds. This cycle is like a long cosmic symphony, with each note representing a star's birth and death. There was another interesting discovery. The Hubble Space Telescope has captured some stunning images of molecular clouds, such as the pillars of creation in the Eagle Nebula. The pillars of creation in the Eagle Nebula, with their strange forms, look like an artist's dreamscape carved out of light and dust. You'll find that exploring the molecular clouds of the Milky Way is like taking a journey through the cosmos. From Orion to Cygnus, from Andromeda to Sagittarius, these molecular clouds exist quietly, yet harbor countless new lives. Perhaps this is one of the most marvelous coincidences of the universe? 5. The double-layered structure of the Milky Way. Did you know? Our Milky Way is not just a simple disk of galaxies, it has a mysterious hidden layer. This mysterious halo acts as an invisible guardian, wrapping around the main disk, and is made up of ancient stars and dark matter, quietly maintaining the stability of the galaxy. If the Milky Way were a sparkling lantern, it is the young stars on the main disk that shine inside the lantern, and the veil outside is the spherical halo. Scientists gradually discovered the existence of this halo as they studied the Milky Way, and the earliest evidence actually came from observing the distribution of old stars. Interestingly, the halo is more than just a decoration. It played a crucial role in the evolution of the Milky Way. For example, as other galaxies approach the Milky Way, the halo acts as a gravitational buffer, reducing the impact of external gravity on the main disk and maintaining the stability of the galaxy. You may have heard of dark matter, that mysterious invisible substance. It's actually one of the components of the halo. Dark matter can't be seen or touched, but scientists have hypothesized its existence by observing the rotation curves of galaxies. Because without dark matter, the stars in the outer reaches of the Milky Way should be rotating more slowly, whereas the actual observed speeds are much higher. One fascinating finding is that the stability of this two-layer structure may be the very key to the Milky Way's ability to last for tens of billions of years. Without the protection of this halo, scientists hypothesize that the Milky Way would have been torn apart by the smaller galaxies and gravitational perturbations around it. Moreover, this halo is not just a passive presence. It actually hides many ancient star clusters within it, some of which are even relics from the early days of the galaxy's formation. Imagine the stars that could be hiding there, billions of years older than the Sun. Research on the halo continues. Some scientists believe that the halo may be divided into two parts: the inner halo, which is more metallic and rich, and the outer halo, which is more ancient and primitive. The discovery of this layered structure further reveals the complex history of the Milky Way's formation. Overall, the two-layered structure of the Milky Way not only makes people marvel at the mystery and delicacy of the universe, but also makes us feel in awe of this house of the universe that has been inhabited for billions of years. 6. Hot bubbles and star formation cycles in our galaxy. What is a supernova explosion? Simply put, it is the final curtain call of a star's life. When a star runs out of nuclear fuel, it may experience an earth-shattering explosion that ejects its matter and energy in all directions. These jets of ejected matter and energetic particles spread out rapidly, forming hot bubbles hundreds to thousands of light-years across. You can think of it as the cosmic version of a water droplet splashing into a calm lake. Each supernova outburst is like a drop of water sending ripples through the surrounding gas. These ripples don't simply spread out and disappear, they have a profound effect on the surrounding environment. A classic example is the local bubble in which we live. Scientists have discovered that this region, about 1,000 light-years across, was formed by a series of supernova outbursts millions of years ago. The density of interstellar gas here is very low, but the temperature is unusually high, as if it were a hot springs area in the Milky Way. When it comes to these hot bubbles, there's more to them than meets the eye. Scientists have found that supernova outbursts not only create spectacular voids in interstellar space, but also drive the circulation of gas in the galaxy. Like the exhaust fan in your kitchen, you can't see the exact shape of the wind, but you can feel the air flowing. This flow is a very delicate balance. If it's too fast, the entire interstellar gas system can become chaotic, like a hurricane sweeping across the land and destroying everything. If it's too slow, the gas that's supposed to be being pushed could stall, impeding the process of star formation. The bubbling action of the Milky Way is comparable to the water cycle in nature. Gas is pushed from one place to another, cooled, compressed, and then heated up again to recirculate. This process releases heavy elements, such as iron and oxygen, from supernova explosions, which become important ingredients in the formation of new stars and planets. You might ask, is this cycle really that important? The answer is, absolutely. By observing other galaxies similar to the Milky Way, astronomers have found that star formation tends to be very inefficient in galaxies that don't have significant gas circulation. It's like a farm field without an irrigation system. There are seeds, but the lack of water simply prevents crops from growing. An interesting story is that at the end of the 20th century, scientists through the Hubble telescope observed some bubble-shaped nebulae regions. At the time, no one knew how these strange shapes were formed. Later, by studying the remains of supernovae, they finally realized that these bubbles were the work of supernova explosions. Even more surprisingly, the gases inside and outside the bubbles are interacting with each other in a cyclical manner. The most amazing thing is that the speed of this gas circulation seems to be controlled by some mysterious rules. It's not too fast, not too slow, just enough to support star formation. This just right phenomenon has scientists wondering. One theory suggests that it may have something to do with the rotation speed and gravitational distribution of the Milky Way. The Milky Way's spiral arms act like a giant blender, pushing the interstellar gas into constant motion. The heat bubbles, on the other hand, are like heat added to the blender, reactivating the otherwise calm gas. The two work together seamlessly, making the entire galaxy like a precision-oiled machine. Although scientists have solved many mysteries about hot bubbles, there are still many unanswered questions. For example, how long do these bubbles actually live? Will they suddenly burst due to some unknown factor? And, are hot bubbles related to the distribution of dark matter? One team analyzing the local bubble found that its edges seem to be highly aligned with the direction of the galaxy's magnetic field. This means that the magnetic field may have played some role in the formation of these bubbles. But the question is the magnetic field strong enough to dominate the movement of gas on such a large scale? These questions are still waiting to be answered. Going back to the original question, why are hot bubbles in the Milky Way so important? The answer is, they maintain the cycle of star formation and provide the Milky Way with a constant supply of life force. 7. Balancing the rotation speed of the Milky Way with the external galactic environment. The rotation speed of the Milky Way is a marvelous value, about 220 kilometers per second. Sounds fast, doesn't it? But on a cosmic scale, it's actually quite modest. It is important to realize that this speed is not arbitrary, but has been tuned by countless cosmic events to be perfectly balanced. If the Milky Way rotated a little faster or slower, we might not see such a beautiful and stable galaxy. The amazing thing about the speed of rotation of the Milky Way is that it is just fast enough to maintain the overall structure of the galaxy without being thrown to pieces by centrifugal force, or torn apart by the gravitational pull of the outer galaxies if it is spinning too slowly. You can think of the Milky Way as a spinning yo-yo, trying to keep its shape while maneuvering in its external environment. How did scientists discover this? Thanks to observations of the surrounding galaxies. For example, among the Milky Way's neighbors, the Small Magellanic Cloud and the Large Magellanic Cloud are two representative examples. Although they are small, but the gravitational effect should not be underestimated. If the Milky Way rotation speed is too slow, these two dwarf galaxies may have taken the opportunity to invade, disturbing the Milky Way's stellar orbit. If turned too fast, the Milky Way may be thrown out of some of its own peripheral stars, and even destroy its own spiral arm structure. In fact, this delicate balance of the Milky Way does not exist in isolation. Its rotation speed is closely related to its surroundings, including other members of this galaxy group. The study shows that the gravitational interaction between the Milky Way and the Andromeda Galaxy also plays an important role. Even though they are about 2.5 million light-years away from each other, the two gravitationally interact like dancing partners, pulling each other yet keeping their distance. Is this just right rotation rate a coincidence, one might ask? In fact, scientists prefer to think that it is the result of a series of cosmic events working together. For example, the Milky Way may have experienced multiple mergers with dwarf galaxies in its early days. These events not only increased the mass of the Milky Way, but also helped it adjust its rotation speed to its current equilibrium. Scientists studying the history of the Milky Way have found that similar galaxies are not uncommon. For example, the Milky Way's close relative, M33, also known as the Triangulum Galaxy, has a relatively fast rotation speed. But unlike the Milky Way, M33 has a simpler gravitational environment, with no nearby neighbors as large as the Andromeda Galaxy. This allows it to rotate a little faster without causing too much trouble. In addition, the rotation speed of the Milky Way directly affects the formation and distribution of stars. By analyzing the stars in the spiral arms of the Milky Way, scientists found that the rotation speed determines the rhythm of star birth. If the rotation speed of the Milky Way is too fast, the gas cloud will be rapidly elongated, or even be torn apart, thus hindering the formation of stars. If the rotation is too slow, the gas cloud will reduce the efficiency of aggregation, is also not conducive to the birth of stars. In terms of star formation, the rotation rate is like the metronome of the Milky Way. This rhythm allows star production in the Milky Way to show an orderly pattern, such as the Orion arm where the Sun is located, which has become a hotbed for star production because of this moderate rotation speed. Now, you may wonder if this delicate balance in the Milky Way means that there is some kind of design in the universe. Scientists answer that although there is no clear designer of the universe, natural laws do play an important role in shaping these structures. For example, astronomers have used computer simulations to model galaxies with different rotation speeds. They found that galaxies that rotated too fast or too slow either became very chaotic or were eventually subsumed by larger galaxies. Only those galaxies that maintained moderate speeds were able to stabilize their existence and spawn complex star systems. Of course, the rotation speed of the Milky Way is not static. Over time, the Milky Way may gradually change its rotation due to interactions with other galaxies. Scientists have found through simulations that when the Milky Way eventually merges with the Andromeda Galaxy, its rotation speed could change significantly. This also means that the current delicate equilibrium is just one stage in the long life of the Milky Way. 8. Interstellar winds in the Milky Way in relation to cosmic dust. When it comes to interstellar winds and cosmic dust in the Milky Way, it's a perfect match. Have you ever thought that these seemingly insignificant winds and dust play a crucial role in maintaining the life cycle of the entire galaxy? First of all, let's be clear about what interstellar wind is. It's not the wind that blows leaves on Earth, but a stream of particles driven by stellar activity. Stars, especially those with huge masses, continue to eject energetic particles into interstellar space through the stellar wind throughout their lives. When these stars come to the end of their lives and go supernova, they generate even larger shock waves that throw out large amounts of material, forming so-called interstellar winds. These interstellar winds not only travel very far, but they're also very smart. Their speed and direction seem to be precisely calibrated by a mysterious mechanism in the Milky Way. What is this calibration? The answer: the rotation of the Milky Way. The rotation of the Milky Way is like a giant blender, blowing these winds in a regular and rhythmic fashion. Then there's the cosmic dust. This dust may seem insignificant, but it is actually the raw material for stars and planets. Dust is mainly made up of elements such as carbon, silicon, and iron, and comes from sources such as the outer layers of stars, supernova explosions, and chemical reactions in interstellar space. Although they're small, they're massive and scattered throughout the galaxy. Now the question arises, how does this dust move through the galaxy? That's down to the interstellar winds. The interstellar winds act like an invisible hand, gently pushing the dust and making it drift from one place to another. And this flow is not random, but guided by the galaxy's gravitational and magnetic fields. As a result, the dust forms spectacular dust clouds, such as the famous Orion Nebula, which is a stellar birthplace filled with dust and gas. Surprisingly, the relationship between the interstellar winds and the cosmic dust is not simply one of push and be pushed. There is a wonderful balance between them. If the interstellar winds are too fast, the dust may be blown too far apart, preventing star formation. If the winds are too slow, the dust may gather too much, leading to a depletion of gas and dust. Scientists have found that this balance is not accidental, but the result of self-regulation during the evolution of the Milky Way. By observing the distribution of dust in the Milky Way and the speed of the interstellar winds, a team of researchers found that the two match up with staggering precision. For example, in the spiral arms of the galaxy, the interstellar winds are slightly stronger in order to push the dust towards the hot spots of star formation, while near the center of the galaxy, the winds are weaker, allowing the dust to be deposited slowly. The process of the interstellar winds pushing the dust around often creates breathtaking scenes in the universe. The Horsehead Nebula, for example, is a region of dust and gas whose peculiar shape was sculpted by the winds. Another example is the Bubble Nebula, which looks like a crystal-clear soap bubble, but is actually a cavity formed by stellar winds pushing dust and gas. Astronomers have also found that the interaction of interstellar winds and dust emits infrared radiation that can be detected by telescopes. By analyzing this data, scientists can trace the path of the dust and even reconstruct a wind map of the interstellar wind. This relationship between the interstellar winds and cosmic dust makes people wonder if the Milky Way is like a sophisticated machine, with every part working perfectly together. What's even more amazing is that this partnership is self-adjusting. If the dust in a certain region starts to decrease, the speed and direction of the interstellar winds will change, sending more dust through. One theory suggests that this phenomenon may have something to do with the galaxy's magnetic field. The Milky Way's magnetic field acts like an invisible highway, guiding the flow of interstellar winds and dust. And these magnetic fields are themselves generated by the rotation of the galaxy and the movement of plasma within it. Although we have gained some insight into the relationship between interstellar winds and dust, there are still many puzzles waiting to be solved. For example, why do the speeds of the interstellar winds vary so much in different regions of the galaxy? How does the ratio of dust to gas affect star formation? And, is there some connection between interstellar winds and dark matter? Some scientists are studying the flow of dust in the border region between the Milky Way and the Andromeda Galaxy. They have found that the interstellar winds there are traveling at higher speeds than expected, possibly as a result of the gravitational interaction between the two galaxies. Such findings may reveal more about the mysteries of the Milky Way and cosmic dust. 9. Supernova debris in the Milky Way and the evolution of life on Earth. Hundreds of millions of light-years away, a cosmic explosion whose effects surprisingly transcended time and space helped life on our planet find its origins. Let's talk about supernovae for a moment. It's a spectacular curtain call at the end of a star's life. When a large enough star runs out of nuclear fuel at its core, it collapses and triggers a huge explosion. This explosion hurls the star's outer layers of material out into the universe at great speed, while releasing huge amounts of energy and new elements. Scientists often say, without supernovae, there would be no us. The reason behind this statement is that supernova explosions synthesize many heavy elements, such as iron, carbon, and nickel. And these elements are the basic building blocks that make up the Earth and life forms. Without them, we couldn't even exist today. In certain areas of the Milky Way, such as the Shipsy supernova remnants, scientists have found large amounts of iron and other heavy elements. These supernova remnants are not only hot spots for astronomy enthusiasts to observe, but they are also important clues for studying the origin of life. By observing these remnants, scientists have discovered that the iron and carbon in them somehow spread throughout the galaxy. These elements gradually spread to more tranquil regions like our solar system with interstellar winds and dust clouds. When our solar system formed 4.6 billion years ago, these elements became the raw materials for our planet. Interestingly, certain elements in supernova debris played a crucial role in the evolution of life on Earth. Iron, for example, is a core component of hemoglobin, which allows our blood to carry oxygen. Carbon, on the other hand, is the building block of life. It's essential for both our cellular structure and complex biochemical reactions. Go back some 3.8 billion years to a time when the Earth was still in a state of chaos. Scientists speculate that some of the chemical reactions of that time may have taken place near hydrothermal vents deep in the oceans. These are rich in iron, nickel, and other metallic elements brought in by supernova remnants. These elements catalyzed the formation of early organic molecules that provided the conditions for the birth of life. If you think about it, you'll realize that there are many hidden coincidences. First, the supernova outbursts were timed just right. If they happened too early, the Earth might not have formed yet. If they happened too late, the chemical basis for life on Earth might have missed the optimal window. Second, the dynamic environment of the Milky Way is also important. Supernova debris needs to be propagated to the right places by interstellar winds that happen to be guided by the rotation and magnetic field of the Milky Way. Astronomer Carl Sagan once famously said, "We are all children of stardust." Not only is this quote poetic, but it also accurately expresses our profound connection to the universe. Modern research has shown that many of the atoms in our bodies, especially the heavy elements, do indeed come from the eruptions of distant stars. Whenever we look up at the stars, we are actually talking to our chemical ancestors. In addition, some research suggests that cosmic rays from supernova explosions may have played a more profound role in the evolution of life on Earth. For example, some scientists have suggested that cosmic rays may have triggered chemical reactions in the atmosphere that alter the climate and environment of the early Earth. These changes, in turn, set the stage for the diversification of life. There are also a number of interesting stories in the research on supernovae and life on Earth. For example, in 1999, a team of researchers discovered an unusually rich layer of iron isotopes in Antarctic ice, which was thought to be a trace left by a nearby supernova explosion. This discovery gave scientists the first opportunity to directly measure the effects of supernova debris on the Earth. There is also a theory that the dinosaur extinction event may have been linked to the supernova. Although this idea is still controversial, it suggests that supernovae may not only facilitate the birth of life, but also have devastating effects. To summarize, supernova events in the Milky Way are not mere catastrophes, but rather opportunities to reshape the universe and nurture life over and over again. This cycle of destruction and rebirth allows us to see the marvelous design of the Milky Way and makes us more connected to the distant stars. 10. The golden position for avoiding disasters. Have you ever wondered why our planet is so secure in its existence? Why does the night sky show us the Milky Way instead of chaos or deadly radiation? Behind it all is actually the result of a series of coincidences and miracles in our galaxy. For example, the location of our solar system is an astronomical miracle. It is right in the golden zone of the Milky Way, about 26,000 light-years from the galactic center. What a concept! Imagine the Milky Way as a giant spinning disk, and our solar system as the one standing at a moderate distance from the center of the disk, neither being thrown out by the frantic spinning center nor being swallowed up by the pitch-black silence of the periphery. And that distance is incredibly ingenious. If we get too close to the center of the Milky Way, the density of stars there is frighteningly high, and the intensity of radiation is even more desperate. That area is filled with gamma-ray bursts, supernova explosions, and a superblack hole, Sagittarius A*, whose gravity is strong enough to swallow everything. Scientists estimate that the radiation levels there would outright destroy any complex life structure. But what if we're too close to the edge of the Milky Way? The stars and elements there are thin, and there aren't enough of the heavy elements, like carbon, oxygen, and iron needed to form life. Without enough heavy elements, planet formation is a problem, let alone evolving life. Our solar system is fortunate to be stuck in this habitable zone, far from the deadly radiation of the core, and with an adequate supply of elements. An astronomer, Richard Boyle, once described this location as the observatory of the universe. Because it's here that we not only survive, but also have a clear view of the structure of the Milky Way. Imagine if we lived near the core of the Milky Way, where the night sky would be almost completely overwhelmed by the light of the stars, making it impossible to see the depths of the starry sky. But now our night skies allow us to look farther out into the universe, and even to speculate about the spiral arms, nebulae, and stellar distribution of the Milky Way itself. Another coincidence is the orbit of the Sun. Not only is our solar system in the habitable zone, but it also follows a very stable orbit in the Milky Way. Some stars in the Milky Way travel through the spiral arm region and enter the stellar dense belt, which can lead to gravitational perturbations, trigger more comet impacts, and perhaps even trigger planetary orbital instability. But the orbit of our solar system just avoids these dangers. It moves around the Milky Way in a nearly circular orbit, like a tuned pendulum, circling the galaxy every 225 million years. Did you know? Scientists once discovered that about 66 million years ago, an asteroid struck the Earth, triggering the dinosaur extinction event. This may have been due to the fact that the solar system passed through certain dense star fields in the Milky Way during its motion, triggering a disturbance of the comet in the Oort cloud. However, the good news is that such events are relatively rare. Most of the time, the Sun stays in a relatively safe region. What's even more amazing is that not only is our Sun stable, but its neighbors are friendly too. The stars in the Sun's neighborhood are not as dense as in some stellar clusters, there are few supernova explosions, and there is no threat of high-energy gamma-ray bursts. If a supernova were to explode near the Sun, it would release a stream of high-energy particles that could strip away Earth's atmosphere and even destroy life on the surface. Fortunately, the Sun is surrounded by mild stars, such as Proxima and Sirius, which are bright and stable. Of course, these seemingly coincidental arrangements are the result of billions of years of galactic evolution. But that doesn't stop us from marveling at these amazing serendipities. Well, that's it for this installment of the program. Welcome to like and comment. Thanks for watching.